Howdy. Chapter 4, Gauss's Law. Why is there an entire chapter devoted to the derivation of this law first arrived by Gauss? There are two reasons. First, this law is extremely useful, but quite sophisticated. It is very possible to use it incorrectly if you don't really understand it. We feel that the best way to understand it is to know where it comes from, which means to know how it is derived. Second reason is that the law is all about a certain property of the vector field E. This property, called the flux or flow of the field, is not unique to electric fields. It will play a critical role in understanding magnetic fields and in circuit analysis. You will also see it in engineering courses dealing with things like fluid flow. That is, in fact, where it was first arrived. To understand the flux of any vector field, we will need to define the area vector associated with an infinitesimally small piece of a surface. This area vector, called ds, has its direction determined by a convention, so it is rather strange. Strange, but useful. There is another quantity needed for the derivation called the solid angle. You may have learned about it in high school, but have forgotten because you have not used it. It will be defined in the chapter. The chapter is then devoted to proving that for any closed surface, the flux of E is equal to 1 over epsilon 0 times the charge contained inside the surface, independent of where this charge may be and independent of any charge outside of the surface. Given that the size of the electric field at any point depends strongly on how far the point is from any charges, this independence is definitely counterintuitive. Although the beauty and utility of Gauss's law is calculating electric fields when we have certain symmetric charge distributions, there's something called the Faraday cage, which is a dramatic application of Gauss's law. If I start this generator, we'll charge up the ball, it will make a huge electric field. The electric field will make these hairs stand on its head. If I had the courage, I would put my fingers on there and my hair would stand up, but although I believe all of these equations, I ain't going to do that. So when I turn this on, we'll see these get charged, repel each other, and stand straight up. When we let everything discharge, all the charge runs off these hairs and they come back to equilibrium. Now, according to Gauss's law, if we put a cage around this, which is called the Faraday's cage, then when I turn on the Van de Graaff, the ball will get charged again, but there will be no electric field inside the cage. We'll dramatically see the effect of the electric field on these strips of thin metal, and I'll put some of that metal inside so that we can see that there's no effect on the metal inside, while there is a dramatic effect on the metal outside. If you go to YouTube, you can find a demonstration where a man actually stands inside such a Faraday cage, turned on a huge Van de Graaff generator, which makes a huge electric field, but it has no effect. The cage makes sure there is no electric field inside. The law in equation form is the integral over a closed surface of E dot ds is equal to the charge inside the surface divided by epsilon 0. The circle on the integral sign means the integral must be over a closed surface. In the next chapter, we will see that this law gives us the easiest way to find an electric field if the charges are symmetrically distributed. This will enable us to find electric potential differences in real devices without doing nasty integrations. It is definitely worth understanding this powerful law. In the problems and exercises in this chapter, you will not have to apply the law, but only convince yourself that you understand the elements of the derivation. You should expect quizzes where you are asked to calculate flux in given situations. Of course, you also need to be able to figure out how much charge is inside a given surface. It would be a pity to miss a problem involving the sophisticated flux over a surface because you did not correctly calculate the charge inside. Summary. The entire chapter is devoted to defining the quantities that enter into Gauss's law and then proving the law. The proof involves area vectors, and since these are part of the definition of the flux of any vector field, it is worth the effort to learn about them. Gig 'em!